Arratsaldeon guztioi, nire izena Jon Errea da eta niretzako placer bat izango da gaur Silvia Bonoli aurkeztea. ¿Vale? Buenas tardes a todos. Y va a ser un placer para mí hoy presentar a Silvia Bonoli. Voy a daros dos cositas, voy a decir en castellano o en euskera, y luego ya presentaré a Silvia en inglés porque la charla suya va a ser en inglés. Es la última sesión del ciclo Jakin-Mina, espero que hayáis disfrutado de él. ¿Vale? Y como es el último, el lunes se os va a enviar una encuesta a vuestro email para que la rellenéis. Es importante para Jakiunde, para saber cómo ha ido el ciclo, para mejorar cara a otros años. ¿Vale? Solo esas dos cosas. La charla va a ser en inglés, podéis hacer luego preguntas en cualquier idioma. Bueno, en euskera todavía, Silvia, no, pronto ya, pero... castellano también podéis preguntar. Y también quiero decir que tenéis mucho mérito vosotros, jóvenes de 16 años, que with all this situation right now in the world, you need to be home and back at 10 p.m. So it's very nice to see some of you here, some of us connected online. So I think you are doing a great effort. And I heard once, a few months ago, a philosopher from Harvard saying that this decade, actually, it's going to be crazy, it's going to be fun. So be patient, be patient. You are doing great. And it's going to be good for you. So, but it's true that now the world is opening to you and you need some role models, okay, for the future. You probably need to decide what are you going to do in the next years, whether you take a science career, science path, or arts path, or whatever. So I think it's important to have role models and references, right? And I think Silvia is going to be, it's a good reference for you, especially women, okay? She's a researcher in astrophysics at the Donostia International Physics Center. I don't know if you know where the Donostia International Physics Center is, in the campus of the University of the Basque Country here in San Sebastian. She's an astrophysicist, okay? She's from Italy. She was born in Bologna, okay? She studied there. She studied actually a degree in astronomy, okay? So actually it's a few of the places in the world where you can study a degree in astronomy. But then she started traveling around the world. She did a master in Toronto in Canada. Then she moved to Munich to do her PhD. Then she worked as a researcher in Zurich and then in Stanford, or the other way around, I don't know exactly.
I will say it later.
Okay.
It's okay.
So she's been traveling around. Then she ended up in Teruel, in Aragon. There is an Centro de Física del Cosmos, where they have an observatory in Teruel with good telescopes. So she was working there. And now, since 2019, he's here at the DIPC. Okay. So she's not only an outstanding researcher, but she's also a mother of two. And she's a woman researcher, a mother, so she has probably, one day you will come across her in the park, okay? So, okay, let's see, we fix the problems.
No sé si es esto. Algo bien, ¿eh? Yeah. A ver.
So I was saying that she's also a mother of two and probably a good scientist, brilliant scientist. So probably one day she has a normal family and we are all normal people scientists, right? So I imagine her with your age, looking at the stars and you know, like the stars always and the universe have always been a source of inspiration, artistic, poetic, scientific. Many big questions were asked looking at the stars, right? But today she's going to talk about things that actually we cannot see, about the dark side of the universe. She's an expert on supermassive black holes. These are the black holes. She will explain much better about these things later, and I hope you will enjoy the talk. So Silvia, the floor is yours.
Thank you much, Jon. Very nice presentation. And bueno, arratsaldeon. I can say a few words, only a few words in euskera. and as Jon said, also later you can ask me questions in also in Castellano, and also during the talk, especially the ones of you that are here, if you want to interrupt me, if you have any question, it's absolutely not a problem, okay? You can always raise your hand and ask me things. There is a bit of noise in the back, maybe, I don't know. Yeah, okay. So, yeah, today I'm gonna talk. Okay, I'm gonna talk about the dark side of the universe. And what do I mean by that? I'm gonna talk to you about three things: about black holes, dark matter, and dark energy, okay? We call them dark, we use dark terms for them, either because they don't emit light, so they're really dark, or because we don't know anything about them, or very little. And so given that it's something we don't know about, it's something obscure, okay? That's why it's the obscured side of the universe. Tengo que estar aquí, si no, no va el micrófono, ¿no? Era para no pisar aquí. Sí, sí. Vale. A ver. ¿Aquí está bien? Pongo este mientras.
Perdona, ¿eh?
A ver. ¿Vale? ¿Está bien? Vale, perfecto. Muy bien. Okay, so, well, Jon already, I wanted to introduce myself a bit more personally, and Jon already did. So, well, I resume it very quickly. I started off in Bologna, where I was born and raised, and where I studied astronomy. Then, after finishing the university, I started a long, that took many years, a long journey on different parts of the world, which often happens in a scientific career. And that can be tiring, but also very nice and very enriching to get to know different people from different cultures, from different places. I was in Toronto, in Canada, then a doctoral student in Munich, in Germany. Then I was a postdoc, a scientist for a couple of years in Zurich and in California. And then, yes, then I arrived in Spain about 8 years ago, first in Teruel, where there is a new observatory that was built recently, a new telescope. If you ever happen to be there, I suggest you to go visit it. It's a very nice place. And then as of 2.5 years, finally, we landed in Donostia. My husband is also an astrophysicist, and he's also at the DIPC. And we have 2 kids who speak Euskera much better than we do by now. And it's a really nice place. You're growing up in a very, very beautiful city. All right, as I said, I'm gonna talk to you about black holes, dark matter, and dark energy. I will talk a bit more about black holes because that's what I work on. But yeah, I want to touch on these 3 topics. Before we get into that, let's talk about the opposite of dark. Let's talk about light, okay? And why light actually is important to study these dark things. What is light? Okay, the first thing we think with light could be a lamp, a light bulb, but also the sun. Yeah, if we go a bit outside, light is everything. So everything that gives us light, the moon in the night, the stars in the night. But light can also be something else, can have a way more poetical touch to it, right? The light can be something inside you, a light, the light at the end of the tunnel, which now it's used a lot during this pandemic. If we see the light at the end of the tunnel of this pandemic, light can be an idea, or if you have studied the Age of Enlightenment, Illuminismo, light is this period after the medieval age where people start using reasoning, start thinking, and where the scientific method started to be developed, right? So in general, light is always associated anyway with something positive, something that gives you, that opens your mind, okay, that teaches you something. For a scientist, light is something a bit less probably poetic. As you probably know, light, we consider light as, light can have 2 forms. Light behaves as a wave, so it has a wavelength and it has an energy, which is associated to the wavelength. But light also behaves as a stream of particles, which we call photons, that all travel at the speed of light, 300,000 kilometers per second, not more, not less. It has a fixed speed. And so that's what light is, right? And light is not only what we see with our eyes, which is really something, what we see of light is really something very small. It's very limited, our sight. Light is much more. Light is the whole electromagnetic spectrum. It's radio wavelength, microwave, infrared, visible, ultraviolet, X-ray, gamma rays. These have long wavelength and less energetic. And as we move, we go higher wavelength and more energetic photons. There is an associated temperature. This is the typical temperature, our temperature, the visible of the light we can see. Colder things have less energy and longer wavelength, and hotter things have a higher wavelength, shorter wavelength and much more energy, okay? Now, why are we so developed in the visible light is because most of the sunlight, our stars, so if this is the intensity of light that the sun emits, sorry, I'm not sure it's visible. Anyway, most of the light is emitted in the visible, okay? And that's where our eyes trained and got more used to perceive the light in this wavelength, okay? But there is a lot of light also emitted in the ultraviolet, which is dangerous for our skin, and that's why we have to put creams in when we are under the sun to not burn, and also in the infrared. Astronomy, the study of the sky, developed in the visible wavelength. We know the sky as we know it, it's what we can see, right? So starting from all the population, all the antique civilizations where they used, well, still now, there are many people that still use stars to guide themselves, right? Or to learn about season, to learn about how, navigate and so on. To Galileo Galilei, who was the first one who developed the telescope, to the most advanced current telescope. This is the one that is in Teruel that I mentioned before. The most classical traditional astronomy has been developed using only the light that we can see with our eyes. But there is much more to it. This is a nice image of a nice galaxy that was observed with the telescope in Teruel. This is another, it's a group of galaxies. But as I said, there is much more to it, but it's difficult to observe it because the atmosphere is protecting us, okay? So we can see well this visible part of the spectrum. We cannot see gamma rays, X-ray, and ultraviolet from Earth because luckily, otherwise we would be dead, the atmosphere is protecting us. So the atmosphere is absorbing those dangerous wavelengths, which are dangerous for life. And so with the telescope from the ground, we cannot observe this wavelength of light. What we can observe are radio waves, but all others, also other types of radio wavelength, infrared, we cannot see them from Earth, okay? And we need actually satellites to observe this wavelength. And it's relatively recent, it's only probably 40, 50 years that we started to have telescopes in space, observatory in space that are looking at the universe with this different wavelength, looking at different types of light. And we have discovered a complete different universe, okay? The universe looks very different in other wavelengths, not in the visible light. This is, for example, a nice galaxy, as you would see with a normal optical visible telescope. But look, if we see it with the X-ray or with the radio, the same thing looks very, very different, okay? This is, in X-ray, you only see the hottest parts of the galaxy, possibly around a black hole, as I will tell you soon later. In the radio, you see other parts of the galaxies, mainly where stars are forming, where there are new stars. So the universe looks very different depending on how you see it. This is another galaxy. It's like a sort of a round galaxy with this dust cloud on front. And this is what it looks like. If you look at this galaxy in the radio, you don't see any of that. You only see a point and then some sort of jets going outside, which, as I will tell you later, are due to black hole. And in X-ray is also very different, okay? So we now, in astronomy, we now know the universe very well, going from radio to X-rays, but there are still parts of the universe that we cannot see, right? Not everything emits light, but there are things that cannot be seen, but they leave some track. And we are using light to find, let's say, these tracks that is other things are leaving. And we are trying to learn more about these things thanks to light. So let's start with black holes. What is a black hole? So to understand what a black hole is, the first thing we need to understand is what the concept of escape velocity. Probably you know, you have studied it in school. Escape velocity is the velocity that something has to have to escape the gravitational attraction of something else. Okay, so for us on Earth, the escape velocity is the velocity that we need to have to escape the gravitational attraction of our planet, of Earth. For Earth, that's about 40,000 kilometers per hour, so 11 kilometers per second. That's the speed approximately we need to have for a rocket to escape completely the gravitational influence of Earth. For the moon, which is less massive, that's less. It's about 8,000 kilometers per hour. For the sun, which is very big, that's about 1.6 million kilometers per hour. So a rocket, to escape the sun, we need to have this velocity, 1.6 million kilometers per hour. So, and this escape velocity, this is the formula, is where the kinetic energy is equal to the gravitational energy. So that's, it does not depend only on the mass, but also on the size of the object, okay? So a black hole is an object so massive and so dense at the same time, in which the escape velocity is equal to the speed of light. So the light cannot escape from it, not even light, and nothing can be as fast as light or faster than light, okay? So a black hole is something for which the escape velocity is 300,000 kilometers per second. To be a black hole, Earth could be a black hole if you could put all its mass in a ball of less than 1 centimeter. If you put all Earth here, Earth could become a black hole. And if you put the sun in the radius of 3 kilometers, probably more or less the size of Donostia, then if you put all the sun, the whole mass of the sun there, then the sun could become a black hole. So black hole is an object with an incredibly infinitely high density, okay? With a very, very high density, and where the density is so high that light cannot escape. So if light cannot escape, if we cannot see it, how do we know that black holes exist? So there are currently 3 ways for which we know that black holes exist. The first one is accretion, then gravitational influence around the black holes, and the third is gravitational waves. And I shortly go through them, okay? What is accretion? Okay, this is a short video. I'm using many videos of the European Southern Observatory. They have a nice webpage with many videos. So imagine that you have here at the very center a very, very small compact black hole. And imagine there is a lot of gas around it. It's like in the sink in your bathroom, okay? You have a sink. If you have water in the sink and the sink is open, water will start going around and falling into the sink, right? The same happens around a black hole. Black hole starts attracting the material around it, which goes around it vertically, like in a vortex at extremely high speed. And let me play it again. And the speed, and the speed at which And because the gravitational attraction of the black hole is so high, the material around it, before it falls down, goes close to a velocity, extreme velocity, very close to the speed of light almost. And imagine some gas, some dust going very fast, particles clashing against each other because they're going really fast. So what happens when you have heat? You produce energy, and that energy is visible, and it becomes really, really bright. So in the universe, when we started looking with the observatory with very special telescopes, we started seeing that there were things so bright that the only way you could explain them is if there is accretion around a black hole. And that's how we discovered that black holes actually exist in the universe. One thing that I study is how black holes are formed in the first place. And also I study in particular quasars, which are very big black holes. As I will tell you later, they're called supermassive black holes. They are more massive than 1 million times the mass of our sun. And we think that there are these black holes at the center of every galaxy. And a quasar is a black hole which is accreting at a very, very high rate. It has a lot of gas around, and we could say it's eating the gas, this very massive black hole. They're eating the gas very, very fast. So they become really, really bright. Here, you cannot probably see it. There is a point there. That's one of the oldest objects known in the universe. It is a quasar. And as you know, in astronomy, when we look, the further we look, the more distance in the past we look, right? Because it takes time for light to travel to us. The light from the sun, it takes 8 minutes to come to us. So the light that we see in a specific moment is the light that left the sun 8 minutes before. So this object, the light that we see today, is the light that was emitted 13 billion years ago, okay? Which is 13,000 million years ago, okay? So when our universe was very, very young, we say it, okay? Was still a kid, okay? So it's like looking in the past. So thanks to these quasars, we can study how the universe was millions and billions of years ago. The second way we know black holes exist is thanks to their gravitational influence, okay? So imagine our solar system. We have the sun and all the planets around. The planets closer to the sun move around much faster than the planets that go outside, okay? That's how just the law of Newton of how gravitation works. Now imagine that you cannot see the sun. Now you close the sun, but you still see the planets going around. Just based on the laws of physics, of the equation of gravity, you can derive, without seeing it, you can derive how big the sun is. What is the mass of the sun? Just by looking at the objects around it. So with the same philosophy, imagine, this is not finishing. Okay. Imagine that you have a black hole that you don't see, but you see stars around it, the stars shine, and you look at how they move around something that is dark, but the way they move, you can estimate, you can have an idea on how big this thing that you cannot see, how big it is. And that's what astronomers have been doing, quite amazingly, by looking at the center of the Milky Way, at the center of our galaxy. With very, very, very powerful infrared telescope, because there is a lot of dust in the Milky Way, and to look at the very, very center of the galaxy, we need to use infrared telescope. Astronomers were able to look at the motion of a few stars around some center that is dark. And they concluded that in this center, in this part, there should be a very compact object, which is 4 million times the mass of our sun. So a very, very big thing, which doesn't emit light. And the only way we can explain it is with what we call a supermassive black hole. And now I put another video, which is very nice. It's a zoom into our galaxy, in our Milky Way, with real images taken by this observatory in Chile. And so we're getting, these are real images of real telescope. We're getting closer and closer to the center of our galaxy. It's very far away, many thousands and thousands and thousands of light years away. And these are the motion of these stars, okay? And again, by looking at how these stars move, that's what astronomers could derive, that there is a black hole there. Okay? No, okay. Now, the third one is through gravitational waves. Maybe you have heard about this because it's been in the news in the last few years. What are gravitational waves? Because of Einstein, I'm sure you've all heard of Einstein, we know that so a mass, what it does, it deforms what we call it space-time. Okay, it's very difficult to really to understand it well, and I myself don't understand it really well. As the first scientists working on general relativity said, only very few people in the world fully understand general relativity. But simply saying it in a way that we can all understand, imagine that you have like a net, okay, a web, and the bigger is an object, the more bent this net is, okay? So the sun bends it a lot because it's bigger. The Earth also bends it, but less, okay? A black hole, it's something that bends infinitely this space. So there is like a big hole there. Now, when two black holes get close to each other, what happens? We say when they merge, when they fuse with each other, what happens is that we start we call it a fabric, this net, this wave, this web. You start having disturbances like waves on a lake, on water. And now, as of a few years ago, scientists were able to detect these waves. So these waves, how do you detect them? You detect difference, that space has changed a little bit, okay? The distance between two things has changed a little bit when one of these waves pass. And this what was first detected in 2015 by an observatory here in the US, but there are also some in other countries. It's a gravitational wave detector. It's an extremely sensitive detector that calculates the space, calculates distances. And for the first time in 2015, it was observed that for a very short time, the space changed a little bit. And that the way the space changed was corresponding to what models, it was first modeled, how we would expect it to change if there are two black holes clashing with each other. And just to give you an idea on how precise this has to be, this has to be so sensitive, which is like measuring the distance to Proxima Centauri, which is the closest star to us, except for the sun. It's a star, which is 4 light years away. It's like measuring 4 light years of distance, which is millions of kilometers, with the precision of 1 hair, okay? So this instrument is amazingly, it's really incredibly sensitive. And that's what scientists managed to do. So now, with all this information, we know that there are many black holes in the universe. And we know that there are 2 kinds of black holes. Stellar black holes, which are just relatively small black holes. They're just few times the mass of the sun. And they're just black holes that come out at the end of the life of a very big star. Okay, like a star when it lives, depending on how big it is, at the end of its life, as we say, could either become a white dwarf, which is what will happen to our sun, or it could become a neutron star, or if it's very big, it can become a black hole. But there is also another kind of black holes, which are the supermassive black holes. And these are black holes which are millions of times the mass of the sun. And we know that we think that they are inside of every galaxy. In every galaxy at the center, there is one of these big black holes. And in our Milky Way, as I showed you before, there is a black hole which is 4 million times the mass of the sun. And the black holes are responsible for all these crazy things, like these really big, powerful jets, because not only they are very bright in the center, but they can also accelerate particles to escape at a very high speed outside the galaxy. Now, let's move quickly to dark matter. Again, how do we know dark matter exists? Okay, how do we know, how we discover dark matter if it's something that, again, we cannot see it? There are two ways it was discovered, and we know more about it. Rotation curves and gravitational lensing, and I will tell you what they are, okay? Let's start with rotation curves. It's a similar principle to what we discussed for the black holes. Imagine that you have, again, something that you don't see. So by studying how stars or some other things that you can see move around it, you know whether it's big or small, okay? It's a big amount of mass or a small amount of mass. This was first pioneered by Vera Rubin. Maybe some of you have heard about her. She was a great scientist, one of the first women astronomer, becoming a professional astronomer, a really great example for all of us. And maybe some of you have seen her in this book, which is quite famous, Women in Science. Also, Los Cuentos de Buenas Noches de Niña Rebelde. Okay, I think she's there as well. So imagine you have a galaxy, okay? So what Vera Rubin did, she started studying the motion of stars around galaxies at progressively larger distance from the center, okay? She studied stars that are close to the center of a galaxy and further out. What she was expected, this red curve, what she calculated is that stars, move depending on how much mass is within their orbit, okay? Like planets do. So stars which are here, they move at a certain speed. As you move further out, the star goes faster. When you get here, which is sort of at the very outskirts, at the last points at the end of the galaxy, of what you can see of a galaxy, the star is what they should be the fastest, but then the few stars that are out should start going slower, okay? Because things that are further away, like our planets, goes as further you are from the mass, the slower you go, okay? Instead, what she found is that stars, or she used also other kind of things, also gas clouds and so on, they kept going fast, very fast outside. And the only way you can explain it is that there is some mass that gives gravitational power, gravitational force, more than what we can see just in the galaxy. There is more to it than what we see. There is actually mass that we cannot see that extends much further out than what we can see, the galaxy. This is a sketch, a drawing of what it will look like. You have your galaxy, and now we know the galaxies are embedded, they are surrounded by a big cloud of what we call dark matter, because it's a type of matter that we cannot see. We know it exists because it can interact with gravity, but we cannot see. It does not emit light, any kind of light. Another way we know it exists is through gravitational lens. I guess you all know what a lens is. So what a lens does, it just bends light. It changes the path of light, making it also an object looking bigger, looking smaller, or looking coming from a different place. That's a similar idea. Imagine that you have a star. Imagine there is another star. This was predicted by Einstein. Imagine there is another star in the middle. This is a bit exaggerated, okay? It's a very small effect. But what happens with the stars in between, these stars bends the rays of light from the stars in the back. So the astronomer that looks through the telescope doesn't see the light coming from there, but it imagines it's coming from there. That's where it sees, so it just extends the rays. The light seems to be coming, and you see two stars. It doesn't see one star, it sees two stars. And that's what has been, okay, sorry. That's also an animation of how this would look like. Actually, if you have a galaxy in front and a galaxy in the back. The galaxy in the back passes, if it shows you how the light would look like from the galaxy in the back because of the ones in the front. So the ones in the front behaves like a lens, and it distorts and changes the way the light from the galaxy in the back comes to us. Okay. Why does it go? Okay. So what astronomers found is that this happens also when you have a galaxy behind a big group of galaxies, like this one. All those small points are a galaxy, okay? It's not really in scale. I make this much bigger and this much smaller, okay? But just to have an idea, imagine that you have a galaxy in the back, and in front of it, you have a group of galaxies. The light of it gets distorted, okay? And you actually see two galaxies that are the same because it's the same one, but you see them coming from different parts, when it's actually in reality is just one galaxy in the back. And again, using physics, using models, you can estimate how much mass you need to create this effect, okay? The more mass you have, the more dramatic this effect is. And astronomers were able to calculate that the mass that you need for this, it's much bigger than what we can see. So again, there has to be dark matter that distorts light, but we cannot see this dark matter. And now we know that our universe is full of dark matter. This is a simulation done by my husband here at the DIPC, in which we are traveling. It's a simulation done in a computer. This is the distribution of dark matter in the universe. There are clumps of dark matter, filaments of dark matter. It looks a bit like the neurons in the brain. And in the parts where there is most dark matter, highest concentration, that's where stars form and where galaxies form and evolve. Okay, galaxies are where most of dark matter is. And that's what we know so far. But again, we don't know what this dark matter is from, where it's coming from. Let me move on. Finally, we talk just a few minutes about dark energy. So to understand a bit dark energy, we need to understand a bit the history of what we know of our universe. Until almost a century ago, astronomers thought, well, at least they knew that the Earth was not the center of the universe. We were a bit more advanced than that. They knew that we had a solar system, and our solar system was inside the big galaxy, okay? But they thought that the whole universe was just our galaxy. They didn't think there was something outside. They could though see some fuzzy things, some clumps of light, a bit diffuse, which we're calling nebulae. And they thought they were just groups of stars inside our galaxy. Only in 1925, soon it will be 100 years, Edwin Hubble managed to measure the distances to these nebulae and realized that these were not part of the Milky Way, but there were other galaxies outside the Milky Way, okay? And he also realized that galaxies are getting further and further away from each other. So the universe was much bigger than what astronomers thought. Actually, now we know that in the universe there are hundreds of millions of galaxies, okay? It's a huge amount of galaxies. And they're getting further and further away in general from each other. There are groups of galaxies in which galaxies are well joined together, but these groups of galaxies are getting further and further away from each other. And that's also what brought the idea of the Big Bang. First the universe was small, compact, and then it started expanding, and that's why galaxies are getting further away from each other. In 1998, these three scientists that won then the Nobel Prize, they discover that the universe not only is expanding, but this expansion now is accelerating. These galaxies are getting faster and faster away from each other. And to accelerate something, you need energy. And we don't know what is causing this acceleration. And because we don't know it, we say it's dark, and we call it dark energy. How did they find out that? So I'll give you this example. Imagine you have a light, okay? If the same light, you put it further away, you see it dimmer, right? You see it a bit more faint. So the further you go, the fainter it is. If you know exactly how much power this light has, you can calculate the distance to these other lights, because if you calculate how much light you see, okay? So you can estimate, I don't know, if this is next to you, you know that this, for example, could be at 3 meters away, this is at 6 meters away, this is at 9 meters away, for example, right? So as these astronomers use the same principle. We know that supernovae, which are an explosion of stars, they always have the same intrinsic light, okay? They have a fixed amount, they emit a fixed amount of light, more or less. So they said, the fainter I see it, the more, the less light I see from them, I can calculate the distance to these things, to these stars. And that's what they did. And in 1998, they found out that some supernovae were more distant than what we would expect. And the only way to explain it is that in between, the space between us and the supernova has been getting stretched in a faster rate than we thought before. So the universe is accelerating. And again, we say that this is caused by dark matter. And this is what our theory right now about the history of the universe. This is not really in scale. It's not in scale. Here, time here is just 500 million years. Here we go this is Spanish, in 9,000 million years. But anyway, we had a big bang at the beginning. Then there was a very big expansion. That expansion started to be a bit slower. The first stars formed. The first galaxies formed. And then 9,000 million years ago, 9 billion years ago, that's where the solar system started forming, okay? And it's approximately around this time when the universe also started accelerating, suddenly started going faster and faster. But we don't know what dark energy is. And this is the composition of our universe. The energy composition, 70% is made of dark energy, 30% is made of dark matter, of matter, sorry, and of all matter, 80% is dark, and 20% is what we say regular matter, which is normal types of particles, molecules of what we see, okay? The stars, galaxies, and dust. So what we can see, what gives light, it's only a very, very small fraction of what is in the universe. The universe is made of many things that we don't know. But thanks to light, we are learning more and more about them. So to summarize, I first told you about the importance of light, because it's only thanks to light that we know about these dark things. We've discussed about black holes. There are black holes small in quotes. They're like they're a few times the mass of the sun, but there are some that are huge. There are 1,000,000 times the mass of the sun. We know that there is a type of matter that does not emit light, which is dark matter. And we also know that there is something that makes the universe accelerate, and that's what we call dark energy. And to finish, because she's, I can say, the mother of dark matter, I wanted to, Vera Rubin, here is also, she was a great role model. So she had 4 kids, and she died a few years ago, and this beautiful observatory in Chile was now dedicated to her. I wanted to finish with some quotes from her. She said, "My life has been an interesting voyage. I became an astronomer because I could not imagine living on Earth and not trying to understand how the universe works. The edge of the universe is far beyond our grasp. Like Columbus, perhaps like the Vikings, we have peered into a new world, which is dark matter, and we have seen that it's more mysterious and more complex than we had imagined. The universe is more complex than what we thought. Still, more mysteries of the universe remain hidden. Their discovery awaits the adventurous scientists of the future, and I like it that way. And I'm sure some of you will be these adventurous scientists that will find out more about these dark things. Thanks.
Thank you, Silvia, very much. Very interesting. So we have time for questions, yes. Euskaraz indezakezue, bueno, euskaraz indezakezue, erderaz sobre
castellano también,
por favor,
lo que sea, ¿eh? Vamos. Si no, empiezo a preguntar yo, ¿eh? A ver, ¿quién había oído escuchar hablar de Vera Rubin? ¿No? Por el libro de las niñas rebeldes, eso, vale. Ahí hay bastantes científicas, algunas científicas, hay más que Vera Rubin. Todos conocen a Marie Curie más, ¿no? Pero hay muchas otras científicas que se merecen ser reconocidas. Y muchas que no han tenido el premio Nobel justo porque estaban trabajando con algún hombre y que se ha sacado el Nobel en vez de ellas, aunque ellas de verdad se lo merecían. Entonces, por eso también me gusta hacer homenajes a Vera Rubin, porque de verdad ha hecho descubrimientos muy importantes, pero por varias razones. Una cosa interesante, cuando las primeras observaciones que hacía en California, en algunos observatorios ahí, no tenían ni el baño para chicas, era solo el baño para mujeres, ¿no? Como pasaba bastante en algunos centros de investigación. Entonces, bueno, ella también eso ha abierto las puertas para que también las mujeres puedan llegar y también ir al baño, ¿no? En esos lugares.
Yo tengo una pregunta para romper el hielo, a ver si alguien más se anima después. ¿Qué candidatos tenemos para Dark Matter? ¿Se supone que es alguna partícula que aún no hemos descubierto? ¿Algunas partículas que aún no hemos descubierto? ¿Eso es lo que más creéis los astrónomos?
Sí, que alguna partícula y también alguna, bueno, se hizo muchas postulaciones, ¿no? Que pudiesen ser también algunos tipos de black holes, de agujeros negros muy pequeñitos que se formaron en las primeras épocas, primera fase del universo. Pero esto por varios tipos de observaciones está bastante descartado. Hay varios tipos, de verdad no soy muy especialista de esto, pero hay algunos tipos de partículas que podrían ser candidatas y ahora hay bastantes experimentos, también en el DPC hay un grupo de física de partículas que está haciendo un experimento en Canfranc, en los Pirineos, para detectar alguna señal, porque estas partículas, aunque no emitan luz, pueden emitir otros tipos de partículas que sí que se podrían detectar, algún tipo de neutrinos, otros tipos de partículas. Entonces hay detectores para otros tipos de partículas a ver si se puede reconducir a la materia oscura.
Another question, beste galderaren bat.
A ver, sobre los agujeros negros, que todos siempre tienen preguntas sobre eso.
Sí, yo tengo una pregunta también, ¿puedo preguntar?
Vale.
¿Se ha visto alguna vez desaparecer una estrella en el centro del universo, de la galaxia? Es decir, porque bueno, ahí se veía como parecían que había estrellas orbitando alrededor del agujero negro.
Aunque estas están muy cerca, están todavía bastante lejos del agujero negro para no ser comida, digamos, ¿no? Hay como un equilibrio muy estable, como es la Tierra alrededor del Sol, hay un equilibrio ahí que es muy estable, ¿no? Entonces, si no mueves nada, todo se queda ahí, en equilibrio. Es cierto que eso es bastante recién, hace unos años, esos astrónomos que estudiaban el centro de nuestra galaxia empezaron a ver que había una nube que se estaba como sí, una nube de material, de gas, de polvo, que se estaba acercando al agujero negro. Y de hecho ha habido un poquito de emisión más. Nuestro agujero negro está como silenciado, tranquilo, no tiene mucho alrededor. Pero en otras galaxias sí que se han visto algunos picos de emisión, y se llaman en inglés tidal disruption events, como básicamente es el agujero negro que saca, que quita, que le roban algo de materia a una estrella que cae o a un tipo de nube de gas que de repente cae más de lo que habría normalmente, ¿no? Sí, se han observado.
Venga, ¿alguna pregunta?
No pressure. De verdad, sin vergüenza, que estamos en familia. Pero bueno, si no si tenéis preguntas también en otro momento.
Si tenéis preguntas también sobre la carrera científica o algo así, también podéis aprovechar.
A ver, ¿quién de vosotros le gustaría hacer carrera científica? A ver, a ti también. A ver, ahora me contáis de qué. Hola.
Hola,
¿Cómo te llamas?
Carla.
Carla. ¿Y qué te gustaría estudiar? ¿O tienes pregunta? Vale.
A ver, pues me gustaría estudiar pues química, biología o así. Y pues la pregunta es que, a ver qué pasaría, o sea, si nos traga un agujero negro.
Ya. Los astrónomos dicen que... ¿Quieres que la repita yo? Que nos pasa si nos come un agujero negro, ¿no?
Sí.
Bueno, cuando algo se acerca mucho, lo que se llama spaghettification. Se dice como, si una persona estuviese cayendo en un agujero negro, se haría más larga, porque la gravedad es tan extrema que nuestros pies, si estamos cayendo así, nuestros pies sienten mucha más gravedad de nuestra cabeza. Entonces, como nos estiran los pies, entonces por eso se llama como si te vuelves un espagueti, ¿no? Bueno, la materia se destruye y ya va adentro, y luego lo que pasa adentro ya no se sabe, porque todavía no sabemos y todavía falta unas leyes de la física que puede explicar exactamente lo que pasa dentro de un agujero negro. No sabemos qué pasa la materia ahí, pero bueno, entra y ya no sale. Ya. ¿Y tú también estás pensando en una carrera científica? ¿En qué?
Yo voy por física, estoy pensando en física.
Ir por física. ¿Qué aspecto de la física te interesa más?
Pues no estoy seguro todavía, pero no sé, me gusta, me interesa. No sé si yo soy una persona que le gustan las matemáticas y así, no sé.
Claro.
O sea, no sé, a la gente suele resultar aburrido o así, pero no sé. A mí me gusta, no sé, soy el distinto, ¿sabes?
La física es algo muy bonito. Bueno, es algo bonito porque tiene el aspecto de matemática, pero es lo que quiere explicar el universo. Y es cierto que muchos lo ven como algo frío, ¿no? Porque algo matemático que no da mucho, no sé, que no tiene muchos sentimientos, pero al final la física es intentar entender el universo y responder algunas preguntas casi filosóficas, ¿no? De dónde venimos, cómo funciona nuestro universo, dónde va a terminar. Y esto al final lo entendemos bien solo si entendemos las leyes de la física. Voy a ver ahí si hay ha surgido alguna. ¿Vas tú? ¿Alguien más que quiere la carrera más matemática científica? ¿O sois más? Yo al final os cuento que yo hice high school, en la secundaria. En Italia un poco es diferente cómo funciona el colegio, pero bueno, los últimos años yo hice ramas mucho más de letras. Estudié latín y griego. En Italia era bastante común todavía. Bueno, todavía el latín sí, el griego cada vez menos, griego antiguo y mucho más filosofía, historia. De hecho, cuando empecé astronomía, mi idea era enfocarme, especializarme en lo que es la arqueología astronómica. Entonces, entender también como los antiguos, cómo entendían el universo, ¿no? Sabían un montón de cosas, aunque no tenían ni instrumentación ni nada. Y me interesaba eso. Luego, bueno, al final decidí más de dedicarme a la investigación. Pero bueno, también si alguno de vosotros ahora sois de letras, igual cambiáis idea o al revés. ¿Tú tenías algo levantado, no? A ciencias. ¿Y qué? Espera, que viene. ¿Qué aspecto de ciencia?
Pues no sé, igual física o algo así.
Vale. Todavía tenéis tiempo, ¿no? Para decir. Bueno, si no hay nada, ¿tenéis alguna otra pregunta? Dime. ¿Tiene que esperar el micrófono, no importa? Como dije.
Sí, hay que esperar porque si no, no oyen.
Vale, si no, no oyen.
Bien, como antes has comentado, en los agujeros negros que están en el centro de las galaxias, hay ciertas estrellas que están las más cercanas, ¿no?
Sí.
Y ha habido un rastro, o no sé, no me sale en español,
Sí.
un pattern
¿Sí?
de las estrellas que van por ahí, que están girando constantemente.
Si quieres en inglés, perfecto, ¿eh?
Bueno, una órbita de esa, ¿se puede saber cuánto tarda una órbita completa de una de esas estrellas?
Sí, a ver, de hecho, una de esas estrellas va tan rápido que aunque hace, a ver, es más o menos como a ver, son muchos años luz, ¿ok? Pero la hace tan rápido que lo hace en 10 años. Creo que una de las estrellas más cercanas hace la órbita en 10 años. De hecho, con todos los estudios que han hecho, acumulando años por año, ya han podido cerrar una órbita de una de esas estrellas. Y hay otra más lejos que se demoran mucho más años, ¿no? Entonces, solo parte de la órbita se ha podido estudiar. Claro, más cerca son, más rápido van. Y la más rápida sí tiene una órbita más o menos de 10, 12 años.
Aquí hay una pregunta también. ¿Por qué no todas las estrellas se convierten en agujeros negros?
Vale, depende, muy buena pregunta, depende del tamaño de la estrella. Básicamente, ¿sabéis cómo es viva una estrella? Una estrella es viva cuando, bueno, emite luz, y emite luz porque está convirtiendo hidrógeno en helio. Las estrellas, digamos, en su periodo de vida normal. Luego explotan, luego hay otros cambios, otros procesos químicos. Básicamente, cuando ya no pueden fundir nada, básicamente es como un reactor nuclear, una estrella, ¿no? Y cuando ya no hay, digamos, material que fundir, que hace que la estrella tenga calor y básicamente es como una bola de gas, ¿no? Y no colapsa porque tiene mucha energía que se genera en este proceso de fusión nuclear, más o menos, ¿no? Cuando eso se acaba, ya no hay energía, no hay que pueda hacer que la estrella se quede grande, la estrella empieza a colapsar sobre sí misma. Una estrella, dependiendo de la masa, colapsa, a ver, como nuestra galaxia colapsa en una estrella, en una enana blanca, que es, bueno, donde los átomos son básicamente muy cercanos el uno al otro. En las estrellas de neutrones, que es cuando hay mucha más masa, y entonces ni siquiera la fuerza de los electrones es suficiente, los electrones colapsan. Sabéis que un átomo está hecho en el núcleo, que son protones y neutrones y los electrones alrededor. Y hay bastante sitio entre los electrones y el núcleo, ¿no?, del átomo. Cuando ya esto se colapsa, se crea lo que se llama una estrella de neutrones, ¿no?, que ya queda solo, está todo muy, muy denso. Cuando hay aún más masa, que ni siquiera estos núcleos de átomos tienen suficiente, digamos, fuerza para resistir la atracción gravitacional, colapsa en algo aún más denso, que son los agujeros negros. Muy bien.
No hay más.
Vale. Bueno, chicos, gracias y terminamos aquí entonces. Si luego surge otra pregunta, mira, estamos en el DIPC y siempre nos podéis